Last time we did something new a couple days ago. We defined a force as 4 words. Kevin, a push or a pull. Anytime you push on something or pull on something, that's a force. It's as simple as that. Now, we also talked about 2 things that a force can do. One of them is accelerate an object, right? We know that. That's intuitive. It accelerates an object. But what does that mean exactly? Well, when we accelerate an object, we can start an object. If it's not moving, maybe it can be started. We can stop an object. If something's moving and you apply a force to it, you can stop it. That's accelerating the object. It's deceleration, but that's a form of acceleration. We can also cause it to speed up or slow down. Or we can also cause it to do what? Which is also included with acceleration. Right? There's your hand up there? Change direction. Good. In the absence of a force, you guys know that an object will keep going forever and ever and ever in a straight line at a constant speed. Straight line at a constant speed. So it's not going to speed up, it's not going to slow down, it's not going to change direction in the absence of a force. A force can cause it to do any of those things. Speed up, slow down, or change direction. All of those things are included with acceleration. What's the other thing that a force can do? You start kind of going back into the furthest recesses of your brain and think, what else can there be? Haven't we said them all? Start an object, stop an object. You're kind of picturing it in your head, and then you're kind of count them off on your fingers. Speed up, slow down, change direction. What else is there? What else is there, Abby? It can deform an object. Good. And what does that mean, really? Well, it means change the shape of an object. Okay, we deform an object, we're changing the shape of an object. Is it impossible that a force might do both? Accelerate the object and deform the object? Sure it is. It's pretty common, actually, to do both. Net force. We talked about the word net and what the word net meant. Total, right? Force, push or pull. The total, push or pull. When we add all of the forces together, some of them might be negative, but when we add all of the forces together, we get a net force. Okay, if I'm applying a force to the left of 20 newtons, and John applies a force to the right of 20 newtons, what's the net force? What's the total force? 0. 20 plus neg 20 equals 0. If I apply a force to the right of 20 newtons and John applies a force to the right of 20 newtons, what's the net force? 40. The total force would be 20 in that case, right? Okay, so the net force is the total force. Total or unbalanced force. When John and I both apply the force to the right of 20 newtons, there is an unbalanced force of 40 newtons, a net force of 40 newtons. When I apply a force one way, John applies a force the other way of 20, the net force is 0. In other words, there is 0 unbalanced force. They balance each other out, right? What's going to happen to the object if the forces balance? Let's say we're both pushing on a desk, both pushing on Spencer's desk. I push one way, John pushes the other way, both with the same force. What happens to it? Nothing. The object at rest is going to stay at rest. Okay? If Spencer's desk was moving and we both applied that same force in opposite directions, what would happen to it? It'd keep moving in a straight line at a constant speed, right? That kind of goes to our next definition, inertia. Inertia is what? From Bill Nye, yeah. Inertia is also what? The tendency of an object to resist a change in motion. In other words, the tendency of an object to keep doing what it's doing. Spencer's desk is at rest. It wants to stay there. Okay, it has a tendency to stay at rest. Okay, a car traveling down the road on 32nd Street right now is moving. It has a tendency to keep moving. It wants to keep moving. Okay, the only thing that's going to cause Spencer's desk to start moving is a force, a net force. The only thing that's going to cause the car on the road to stop moving is a net force. So inertia is the tendency to keep doing what it's doing. You guys remember what the word static meant versus translational? Forget about equilibrium for a second. Static meant No. At rest, not moving. Translational means moving. Equilibrium means balanced. So if we say static equilibrium, we mean balanced at rest. When we have an object that's at rest and it's not moving, it's in static equilibrium. The forces are balanced. Okay? The forces must be balanced. If the forces weren't balanced on Spencer's desk right now, what would happen to her desk? If there was an unbalanced force on her desk, what would happen to it? It would move. It would accelerate. It would speed up. Translational equilibrium is balanced forces when the object is moving. Balanced forces, object is moving. What happens when you have balanced forces and the object is moving? Here's an object on the ground. It's moving to the right. We apply another force to the right of 10 newtons. We apply a force to the left of 10 newtons. What's going to happen to that object that was already moving at 5 meters per second? It's going to keep moving at 5 meters per second. What do you got to do to it in order to cause it to speed up? Yeah. If it's moving to the right at 5, you got to make this one 20 newtons. Okay, if you want it to slow down, what do you got to do? Right. Let's make this one 20 newtons or 15 newtons or something that's bigger. You need an unbalanced force if you want it to speed up, slow down, or change direction. In other words, you need a net force, a total force that's not zero. Newton's first law. It's the last thing we talked about. Newton's first law has two aspects to it, 2 points to it. We've talked about both of them already, except not in this context. An object at rest wants to stay at rest forever until it's acted upon by an unbalanced force. Not until acted upon by a force. Spencer's desk is at rest right now. There's a force acting on it, gravity. But it's not moving because something balances gravity. And we'll talk a little bit later today about what that force is that balances gravity. John pushes to the right on her desk with the force of 20 newtons. I push to the left with the force of 20 newtons. It doesn't move. It wants to stay at rest until an unbalanced force is acting on it. Even though there's forces, it's not moving because there's no unbalanced force. The second aspect is an object in motion wants to do what? Yep. Good. An object in motion wants to stay in motion in a straight line at a constant speed until acted upon by an unbalanced force. Okay, the first one, an object at rest. One of the examples that we did the other day, Tuesday I think it was, when we went over this for the first time, was the little demonstration with the placemat, right? We had the placemat underneath the plate, and the fork, and the knife, and the cup of water. We pulled the placemat out from underneath the plate, and the fork, and the spoon, and the whatever, the cup of water, whatever was there. The objects at rest, the fork, and the glass of water, and so on, they're going to stay at rest forever until acted upon by an unbalanced force. I pulled that placemat quick enough that it didn't apply an unbalanced force to those things, therefore they didn't move anywhere. They stayed at rest. Okay. Another one that I gave you was sitting at a stop sign. Okay, I told you guys years ago, 15 years ago, I was sitting at a stoplight in Calgary and somebody hits me from behind. Your body now has an unbalanced force acting on it, so it starts moving, right? But your head, at least for a brief time, doesn't have any unbalanced force. So what happens to it? Yeah, no, your head doesn't go back as your body goes forward. Your head stays at rest. Your body goes forward, your head stays at rest. That has the effect of this. Your head doesn't go back like this. Okay, your body goes forward like this and leaves your head back where it was. Okay, it has the same effect as your head being pushed back. Okay, but strictly speaking, your head is remaining at rest until your neck applies a big enough force to pull it forward, which by that time is probably giving you whiplash. An object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. I gave you the example of this one the other day as well. When I was your age, or maybe a little bit older, coming off the highway onto an off-ramp, okay, in a snowstorm. I come off the highway right here, I slow down, not slow enough, hit a patch of ice, do this, until I went in a straight line at a constant speed. I was going maybe 30 kilometers an hour. I kept going in a straight line. I kept going at 30 kilometers per hour until I hit that guardrail. Okay, until I hit the guardrail, until there's an unbalanced force that keeps me from going in a straight line and that keeps me from going at the same speed. Okay, an object in motion stays in motion, straight line, constant speed until acted upon by an unbalanced force. All right? Easy stuff, right? We had 5 questions for homework last night, page 142, number 1 to 4 and 6. We assigned them on Tuesday, 2 days to do these 5 questions. So you guys should have done a bang-up job on these, having 2 days to do them. Which question or questions would you like to go over here? Okay, let's do number 6. Any others? No? 6 is it? All right. Imagine you were the hockey coach for a team of 10-year-olds. At a hockey practice, you ask the players to skate across the ice along the blue line. So let's draw this here. Okay, here's the end of the ice. Okay, here's the goal line, okay, with the net in front of it. And then here's the blue line up here. You ask the players to skate across the ice along the blue line, and you shoot the puck into the empty net. Most of the shots miss the net. The faster the children skate, the more they miss. Newton's first law would help the players understand the problem, but a technical explanation might confuse them. In other words, okay, we're not going to explain to these 10-year-olds that an object in motion stays in motion at a constant speed in a straight line until acted upon by an unbalanced force. We want an explanation that would make sense to the 10-year-olds. Anyone? Okay, put your hand up. No? You guys aren't that far from being 10. You guys should have something here. Dustin, what's your explanation? Okay, that's a pretty good one, yeah. The faster you move across the blue line, the faster the puck wants to move with you. So as you shoot the puck, as you're moving to the right and you shoot the puck, what's going to happen to the puck? It's going to go to the right. Make sense? That's a pretty good explanation for 10-year-olds. Okay, smart 10-year-olds would get that. What it will be, with the aid of a diagram, design a drill for the team that would help the players score in this type of situation. Some of you guys are hockey players. How about we just put the puck somewhere else? Okay, instead of putting the puck in front of the net and shooting right at the net, okay, put the puck in front of the net, moving this way, shooting this way, and having the puck go this way. How about we put the puck back here? Okay, let's put the puck back here. If we're moving this way and we shoot the puck this way, now maybe the puck will go this way into the net. Or, alternatively, this is almost a vector analysis from the last unit, right? If the puck is right here and you want to shoot the puck in the net and you're moving this way, where are you going to shoot it? If we want the puck to go down here, we don't want to shoot it down there, right? We're going to shoot it this way. So it's kind of awkward, but as you're skating across there, right? There's the net right there, okay, where the map is in the back of the room. As you're skating across here, instead of going like this and shooting like this and have it miss the net over there, you're going to go across like this and then shoot kind of back like this, okay, as if you're shooting in the back corner there. And just maybe you'll put it in the back net there. Okay, good enough? Excellent. Okay, let's move on. Acceleration is the rate of change of velocity, how quickly you're changing velocity. What does it depend on? What 2 factors will affect how quickly something will accelerate? Well, I can see what you're saying there, okay, and you're not completely wrong, but you're not looking deep enough, not looking fundamentally enough. Okay, does velocity affect acceleration? Does the change in velocity affect acceleration? By the equation, yes, it does. A is equal to delta V over delta T, right? The problem is, it's not velocity that affects acceleration. It's the acceleration that affects the velocity, right? How fast you're moving doesn't affect your acceleration. How much you're accelerating affects how fast you're moving. Okay, does that make sense? So you're not way off base on that, but that's not exactly what we're looking for. There's two factors that affect directly how quickly you accelerate. You should be able to guess one of them because we've been talking about it for the last 2 days. Joe? Force. The force. You apply a bigger force, you accelerate it quicker, right? You apply a force of 5 newtons on this desk. Okay, maybe it moves a little bit. You apply a force of 50 newtons on this desk, and it moves a lot quicker. It accelerates at a lot quicker rate. So fundamentally, the acceleration is dependent upon force. And that's a direct relationship. In other words, as force goes up, as force increases, acceleration will also increase. What else affects acceleration? You may experience this tonight. There's snow outside today. You may have to go home and you may have to push your neighbor out of the driveway. They may be stuck as they're going out onto the road with all the snow on the road or whatever. If you have to push that car out of a stuck spot on your street, what characteristic of the car what characteristic do you hope that car has? Yeah. You hope it's lighter, right? Because something that's heavier is harder to accelerate than something that's lighter. The other thing that affects acceleration is mass. Now, as mass goes up, what happens to the acceleration? The acceleration goes down. The acceleration decreases. I push harder, I accelerate quicker. I get heavier, I accelerate slower. Newton's second law is essentially what we just said, right? We just said that acceleration depends upon mass and force. As force goes up, acceleration goes up. As mass goes up, acceleration goes down. The second law is stated technically as the following. The acceleration of an object, can't spell it, acceleration, there we go. The acceleration of an object is directly proportional to, and what that means is that as one goes up, the other goes up, directly proportional to, and in the same direction as the net force. In other words, F is directly related to, A is directly related to F. As F goes up, A goes up. And it's inversely proportional to the mass. In other words, as A goes up, or as mass goes up, acceleration goes down. Put these two together, we get an equation for acceleration. Our sixth group B equation. Remember our group A equation? V is equal to delta D over delta T. Then we had all these other group B equations. Here's another group B equation. A is equal to F over M. That F isn't just any force. Okay, keep going back to this example, but we'll go back to it again here. John pushes on Spencer's desk with a force of 50 newtons. I push on it the other way with a force of 50 newtons. It's not the 50 newtons I want to plug into that equation. It's the zero that I want to plug in, the net force, the unbalanced force. So the acceleration of Spencer's desk would be zero because the net force is zero. John pushes with 70 newtons. I push with 50 newtons. Okay, the net force is now not 70 or 50. The net force would be 20 newtons. And as the net force is 20 newtons, that's the value that we plug into this equation. A is equal to F over M. We know what units A is, right? Meters per second squared. What units is mass? First time we've used mass. Yep. Kilograms. How many people take chemistry? If you take chemistry, mass is usually measured in grams. Forget all about chemistry. Never going to use that. Okay, mass should be measured in kilograms. Now, you use grams in chemistry because usually you're dealing with really, really small quantities, right? It makes sense to use grams in chemistry when you're dealing with small quantities. In physics, we're usually dealing with bigger quantities here. So we use something that's more convenient for us, kilograms. F would be the net force. Do you know what units net force is measured in? Sure you do. Newtons. It's named after Newton, Isaac Newton. So now we get two laws. Object at rest wants to stay at rest forever until acted upon by an unbalanced force. Object in motion wants to stay moving, constant speed, straight line, until acted upon by an unbalanced force. Now we also have the acceleration is directly proportional to and in the same direction as the net force, and it's inversely proportional to the mass. As F goes up, A goes up. As M goes up, A goes down. Here's an example. A cross player exerts an average net horizontal force of 2.8 newtons forward on a 0.14 kilogram lacrosse ball while running with it in the net of his stick. Calculate the average horizontal acceleration of the ball while in contact with the lacrosse net. Hey, by the way, is force, is acceleration a vector or a scalar? Vector. Is mass a vector or a scalar? Yeah, because there's no direction with mass, right? So this is a vector, this is a scalar. What do you think force is? Yeah, it's a vector as well. So a vector is equal to a vector over a scalar. Let's find the acceleration here. First of all, our net force is 2.8 newtons. Our mass is 0.14 kilograms. And we want to find the acceleration here. Well, this is an easy question, isn't it? A is equal to F over M. We got 2.8 newtons divided by the mass of 0.14 kilograms. It's going to give me 20 meters per second squared. Which way is the acceleration? Well, if the force is forward, then the acceleration will also be forward, because the acceleration is always going to be in the same direction as the force. Good? Yeah. That's a good question, hey? How does newtons divided by kilograms give you meters per second squared? Right now, unfortunately, you're going to have to just trust me on it, okay? But it won't be all that long before you can ask me that question again, and I'll be able to give you an answer. Okay, right now, to derive how those two end up being the same, it's not all that difficult, but I end up using things that we haven't seen yet. Okay, they are the same thing. Okay, but and I'm not asking you to trust me forever, but once we've done a little bit more stuff, then I'll get you to remind me about that question. We'll try to do it again, okay? Okay, let's take a look at those two questions. Please see what you can do with those real quickly here. Okay, guys, if we're okay with these two questions, let's move on to one more last thing that I want to do today. Today we're going to talk about 4 types of forces. So we know what a force is. We know what a net force is. Okay, we talked about when you have more than one force, you add them up, you get the net force, the total force. But what are some of the types of forces that we can have? If we have 2 or 3 or 4 forces acting on an object, what's causing those forces? What kinds of forces are they? Well, the first type of force that we're going to talk about is called your weight. I guarantee you right now, when we have a test, and you're asked for essentially the difference between weight and mass. You're asked for the weight of something. Some of you are going to put 70 kilograms, whatever. Wrong. Mass is measured in kilograms. Mass is the amount of matter that you possess. Mass is the same wherever you go in the universe. I weigh 70 kilograms. I weigh 70 kilograms on Earth. I weigh 70 kilograms on the moon. I weigh 70 kilograms on Jupiter. I weigh 70 kilograms in the space station. My mass doesn't change. The amount of matter that I possess is the same no matter where I go. Weight, on the other hand, is a force. Weight is a force of gravity acting on an object. That's not measured in kilograms. That's measured in newtons because it's a force. It changes depending upon where you go in the universe. Okay, I weigh about 700 newtons on Earth. I weigh about 100 and something newtons on the moon. I weigh something different on Jupiter. I weigh virtually nothing, okay, in a spaceship that's traveling towards Mars. My weight changes because it's the force of gravity that acts on the object. And the force of gravity, okay, any force is equal to m times a, but specifically the acceleration that I would use for this would be negative 9.81, or we'll just make it positive actually so that we get a positive value for weight here. Positive 9.81 meters per second squared. My mass is 70. My weight is 70 times 9.81. That's my mass on the Earth. It's my weight, sorry, on the Earth. My weight on the moon is 70 kilograms. My mass on the moon times 1.6, the acceleration due to gravity on the moon. I forget what the acceleration due to gravity on Jupiter is, something like 20. Let's say it's 20 anyways. Okay, my mass on Jupiter is 70. My weight is 70 times 20. What's the quickest way to lose weight? No, don't go to Mars. Mars is a 2.5 year return trip. Don't go to Mars. Go to the moon. You lose 5/6 of your weight. It's like better than the Atkins diet, better than everything else diet combined into one. You become 1/6 of what you were before. You don't lose any mass. You don't get any smaller, but you weigh a lot less. The only problem is if you want to come back, then what's going to happen? You're going to gain that weight right back. Well, you might. They almost died in Apollo 13 there, right? But not quite. Your weight changes because it's dependent upon gravity. Your mass doesn't. Even on Earth. Look, on Earth, in Vancouver, I have a mass of 70 kilograms. At the top of Mount Everest, I would have a mass of 70 kilograms. But my weight in Vancouver would be more than my weight at the top of Mount Everest because G, the acceleration of gravity in Vancouver, somewhere around 9.82. At the top of Mount Everest, somewhere around 9.7. Okay, so because the acceleration of gravity is less at the top of Mount Everest, my mass isn't going to change, but my weight will. Make sense? Remember this. The next time you're asked for weight of a 70 kilogram object, don't say 70 kilograms. Don't think, oh, that's a trick question. I got this one. 70 kilograms. No. The mass of a 70 kilogram object is 70 kilograms. The weight is 70 times 9.81. The next force is the normal force. And this one is completely foreign to you. Weight, you've heard of before, obviously. You've dealt with weight a number of times, even though you might not have known exactly what it means. Normal force is completely foreign to us. What's happening to Tyler's desk right now? What's happening to your desk right now? Nothing. It's not moving, right? Nothing's happening to it. Good. So what's the net force acting on his desk right now? 0, right? Because if there was a net force, what would happen to it? it would start moving, right? It would accelerate, right? Well, there's gravity acting down on his desk. Would you agree with that? Gravity acts down. So if gravity is the only force acting down, what should be happening to his desk right now? It should be falling down. It should be moving down through the floor. But it doesn't. So there must be a force that counters that force of gravity. There must be a force that opposes that force of gravity. We call that the normal force. Normal in physics, the word normal means 90 degrees. In physics 30, we're going to talk about something called a normal line, which is not a normal force at all, but it's a line that is at 90 degrees. So normal means 90 degrees. The normal force is the force that acts up. I'm going to put up in quotation marks because it's not necessarily up. I'll give you an example of when it's not up a little bit later on, but for all intents and purposes, it's usually up. Force that acts up at 90 degrees from the ground. But I'll put ground in quotation marks as well because it's not always the ground. Right now, there's a force of about 1,000 newtons acting down on Tyler's desk, the force of gravity. There is a normal force, the ground pushing up, with a force of 1,000 newtons. Because if gravity was bigger than the normal force, the desk would fall down. If the normal force was bigger than the gravity, what would happen? It would float. It would rise up, right? It would rise up into the air. It's the ground pushing up on his desk right now at 90 degrees. Give me an example of when it's something that pushes up. Okay, something that provides a normal force, but it isn't technically the ground. It's something else. Yep. A shelf. Good. A shelf provides a normal force on a book, right? A shelf provides a normal force on a book. The shelf is pushing up at 90 degrees. Okay, the gravity is pulling down on the book with a certain force, right? Those two forces balance each other out, the normal force and the force of gravity. Okay, it's like the force of the ground pushing up on Tyler, but it's not the ground, it's the shelf. Perfect example. Give me an example of a situation where the force isn't pushing up, but rather it's pushing some other direction. It's the ground or it's the shelf or whatever, but it's not pushing upwards. It always pushes at 90 degrees. It doesn't always push upwards. What if you have a hill? Here's the object on the hill. Gravity acts down, right? Always, straight down. The normal force acts not straight up, but at 90 degrees to the hill. How about this one? You guys will all experience this. At least I hope you all experience this. When we go to West Edmonton Mall at the end of May. You're going to roller coaster loop upside down. What provides the normal force on this cart? It's not the ground. What provides the normal force on this cart? The track. Which way does the normal force act? Not up. Which way is the track pushing? The track is pushing down on the cart there, right? So usually the normal force is up, and usually it's provided by the ground. But sometimes it's provided by a track, and sometimes it's not acting up. Sometimes it's acting at an angle, sometimes it's acting straight down. But it's always 90 degrees. Yep. Yep. No, that's a good question. In fact, it's just the opposite. It's just the opposite. By space, I assume you mean like something like the International Space Station orbiting around. You know how far away from us the International Space Station is when it goes overhead? And it does go overhead to us, by the way. Sometimes you can actually see it. Do you know that? You can actually see, if you go on NASA's website, you can, type in your city or your town, Okotoks, Alberta, or Calgary, Alberta. They'll give you dates and times of when the International Space Station will be overhead. Okay, and you can look up. If it's dark, you can see it. You can see it very, very clearly if it's a clear sky. Now, it's a bright light. You can't see details, like you can't see anybody waving out the window or anything like that, but you can see it very clearly. You know how far away it is from us? It's 400 kilometers away. Okay, Edmonton is as close to us, is no further away from us, or sorry, is as close to us as the International Space Station. It's 400 kilometers away. That's it. Now, Edmonton's easier to get to than the International Space Station, but it's just as far away as the space station is. There is lots of gravity in the space station. Gravity in the space station, acceleration due to gravity is about 9 meters per second squared, or almost 9 meters per second squared. It's almost as much as it is on gravity. So why are they floating around? It's not because there's no gravity up there. There is. There's almost as much gravity as there is here. It's because there's no normal force. There's no normal force. Now, what gravity truly is and what we perceive as gravity are two entirely different things. Okay? Gravity is the force of the earth pulling us down. We don't feel that. You don't feel the force of the earth pulling you down right now. You don't. What do you feel? You feel the force of the ground pushing you up. But the only reason the ground is pushing you up is because the earth is pulling you down. So those two forces balance. What do you feel as gravity? Well, about 60 kilograms times 9.81. Okay? But that's because that's the normal force that acts on you, not because it's actually gravity acting on you. When you're in the space station, you're orbiting around the Earth. I'm going to erase a little bit here so we can draw this out here. When you're in the space station orbiting around the Earth like this, gravity pulls you down. Otherwise, you wouldn't orbit around. If gravity didn't pull you down, you'd go off in a straight line. Gravity pulls you down hard. In fact, it pulls you down so hard that you want to go in a straight line. Gravity wants to pull you down this way. You go down this way. You want to go in a straight line. Gravity pulls you down this way. You go this way. Okay? You want to go this way. Gravity pulls you down this way. You go so on, right? You're free falling the whole time. You're in the space station for 6 months. It's like going up in a drop of doom ride, one of those free fall rides, where you free fall for like 3 seconds, except you're free falling for like 6 months. When you free fall, gravity's still acting on you, but there's no normal force acting on you. So although there's gravity, you don't perceive gravity. And what happens? You float around. That make sense?
What happens if you're outside
The atmosphere is irrelevant, okay, whether you experience gravity or not. But what happens if you're so far away that gravity is effectively zero? And that can happen, yes. Now, people have never been that far, but it is conceivable sometime that they would be. Okay, if you're way off in space, way off in space, and there will be always gravity, but if you're far enough away, there'll be virtually no gravity. Then there's not going to be gravity, but there's also not going to be a normal force, right? As long as there's nothing pushing you on you, there's no normal force, and you don't feel gravity. In deep outer reaches of space, there is no gravity, so nothing pushes back on you. Okay, when you're free falling, as you do in the space station, there's gravity, but nothing pushes on you because you're free falling. As the ship free falls, you free fall with it, and nothing pushes on you. You don't perceive gravity; you float around. They have NASA has this airplane. It's a 727 jet. They nickname it the Vomit Comet. Yeah, it's an airplane that goes as high as a 727 can possibly go safely. Okay, it reaches that peak height. And then it dives down towards the ocean. And then it actually follows a parabola. It doesn't kind of go straight down, but almost straight down. Because it's free falling, straight down, almost straight down, gravity's still there, clearly. But there's no normal force acting on you now because it's free falling and so are you. The walls of the airplane or the floor of the airplane don't push on you. What happens to you? You float around. How many people have seen the movie Apollo 13? The space scenes in Apollo 13 where they were floating around, and that was the first movie they ever did this. Prior to that, it was always like little invisible ropes that, like strings basically that held people up, and it looked fake sometimes. Okay, in that movie, they actually shot a good part of that movie in this Vomit Comet, the NASA Vomit Comet. Okay, so they were actually floating around. When they're floating around in the movie, they really were floating around. They had to do hundreds of takes because they would get 30 seconds of film at a time before they had to do it again. Okay? But again, there is gravity there. There's just no normal force. Yep. More? I thought I saw your hand going back up. No? What happens? That's a good question. What happens when you go back up? Well, I don't know this for sure, but I would suspect that when it goes down, it's probably not going to go right back up. Like it's probably going to land, and they do some stuff, and then it goes back up again. So it probably goes up from the ground, I would think. But in the end, when an airplane goes up, when an elevator goes up, for that matter, what do you feel? You feel heavier. Why? Because the normal force is pushing on you harder than gravity to get you up into the air, right? You ever notice when you start off in an elevator on the ground and it accelerates quickly? How many people have ever been in the CN Tower? Or a really tall building like the CN Tower? I was in the World Trade Center, by the way, just a few months before it was actually crashed into and came down. I stood on the roof of the World Trade Center, actually, just a few months before planes crashed into it. It's a high building. It was 112 stories. CN Tower is even taller than that. Okay, as you accelerate upward in one of those tall buildings, because the elevators have to move fast, right, in buildings that high, as you accelerate upward, you feel heavy. But you're not any heavier. You just feel it because the normal force is pushing on you harder than gravity is. Usually, normal force and gravity are the same. So if I weigh 700 newtons, I feel like I weigh 700 newtons. But if I'm falling, I feel lighter because normal force is smaller. If I'm going up, I feel heavier because normal force is bigger. Okay? Yep. Go ahead. Yep. Friction is our next force. Today's a good day to talk about friction when there is pretty much no friction outside. I drove into school this morning. I got up about 6 this morning, looked out the window. It was fine. There's a tiny little skiff of snow outside. Not bad at all. It wasn't snowing. When I came into school around 8:15, driving up 32nd Street, the traction control on my car was going nonstop. It was making that noise of the traction control pretty much nonstop coming up the road. It was slippery. Yeah, I assume it probably still is. When you're driving on pavement, whether you know exactly what friction is or not, we all somehow intuitively know that there's friction. When we're driving on ice, we somehow know intuitively that there is very little friction. Friction is a resistive force. It's a force acting between two surfaces that resists motion. Usually there's a force acting between the road and your tires that resist motion? Wait a second. It doesn't resist motion, does it, when you're driving? Yeah, it does actually. Do your tires spin on the pavement? No, so the friction resists the motion between the tires and your pavement, right? That's what actually allows you to move. Believe it or not, the force that resists motion between your tires and the pavement is actually what propels you forward. What about when you're on ice? Is there a force that resists motion between your tires and the pavement then? No, or at least it's a lot smaller. So that's when you slide, right? Can't stop. Can't even start, really. Can't even drive forward because your wheels spin because there's no resistive force. There's two kinds of friction. We'll talk a lot more detail about these tomorrow. One's called static friction. Static friction is the force of friction that prevents an object from beginning to move. There's a force of gravity acting down on Spencer's desk right now. There's a normal force pushing up. If I push on it with a force of 5 newtons to the left, it doesn't move. Well, there must be a force of static friction of 5 newtons to the right resisting that motion. Does that make sense? Preventing it from beginning to move. The other current is called kinetic friction. Kinetic friction is the force of friction that resists motion of an already moving object. When you're driving your car and you slam on the brakes and you skid on the pavement, kinetic friction is what stops you. Okay, it resists the motion of an object that's already moving versus the static friction that was trying to keep it from moving in the first place. Static friction is usually bigger than kinetic friction. You ever notice that when you're trying to push something, it's harder to lift up the pencil for a second so I don't make a mess of your notes there. You ever notice, I just don't want you to write because I don't want to make a mess of your notes as I push your desk here. You ever notice that sometimes it's like, I can't get this moving. I can't push this thing. It's too heavy. And then all of a sudden when you get it moving, it's like, oh, it's so much easier to move once it's moving. You ever notice that? Because static friction is bigger. The force that keeps it from beginning to move is bigger than the force that kind of slows it down after it's already moving. Again, we'll talk more about that tomorrow. This isn't a force. This is a diagram. It's a picture. It's the last thing we're going to do today. A free body diagram. Yep, go ahead.
The more friction there is, the more force will be to propel us up.
In a car, you mean?
The car, in the car that is.
Yeah.
Does that work in any other aspect?
Well, no, it wouldn't work in every aspect. The question for those of you who didn't hear is, the more force of friction there is, basically the better we'll move. Okay? No, that wouldn't work in all scenarios. It works with wheels. And the reason it works with wheels is because, let's take a look at, here's a wheel. Okay, here's the road. Okay, here's a spot on the wheel. Okay, you make a little chalk mark on a wheel. Okay, that little chalk mark can't slide along the surface. If it does, okay, if that little chalk mark, if that wheel kind of slides from left to right or right to left, then we're not going to start moving, right? Because that's when your wheel is starting to spin. We need this spot on the wheel to make contact and to stick well to the road. That's static friction because it's not sliding, it's not moving, it's rotating, it's not moving. Now, the better friction is, the better it sticks, the more acceleration you're going to get, right? Because you're going to be able to put your foot on the gas pedal even more before your wheel starts spinning. But that's not the case in every situation, right? Only with spinning things like that. Okay? If Spencer's desk has a maximum force of static friction of 50 versus 25, well, it's not going to go as easily with a force of friction of 50 as it is with 25, right? Because it's harder to overcome 50 than it is to overcome 25. That make sense? So in the case of wheels, yeah, you want to have a bigger force of friction. In the case of just pushing something and sliding it, you want to have a smaller force of friction. Snow tires, right? We have snow tires. Slam on the brakes, they stick better to ice, right? But it's also not just for slamming on the brakes, it's for putting your foot on the gas pedal, right? The rubber is designed to stick better to ice when you're starting as well. When you're skating, on the other hand, you want to have a lower friction so you can slide better. Okay, free body diagram is a diagram that shows all forces acting on an object. That's it. It shows all of the forces acting on an object. In a second, we'll do one example of a free body diagram, and then that's it for us. So what you got to do when you see a question where they ask you to draw a free body diagram is look at what force, ask yourself what forces are here. Is gravity acting on it? Is a normal force acting on it? Is somebody pushing on it? Is friction acting on it? Is, and so on. Like, what forces do I have acting on it? And then draw them. Draw those forces as arrows. If the force is bigger, draw it as a longer arrow. If the force is smaller, draw it as a It's a shorter arrow. Take a look at this one here. It says, draw a free body diagram of a 20 kilogram object that's sliding on a horizontal surface. Here's my horizontal surface. Here's my 20 kilogram object. Technically, in a free body diagram, I don't even need to show that it's 20 kilograms, but I usually do. A free body diagram technically just shows the forces. All right. Sliding on a horizontal surface, it's pushed with an applied force of 30 newtons, and it's resisted by friction of 10 newtons. Let's say I'm pushing it to the right. We'll call that FA, the applied force of 30 newtons. My friction is going to act which way? The opposite way. It resists motion, right? Notice I'm drawing that quite a bit shorter. How come? It has to be somewhat to scale, right? It's a smaller force. It's a shorter vector. Luis? Oh, okay. Like, why don't we draw the applied force over here? We can. We can. It doesn't matter where you draw the forces, okay? That's a good question. It doesn't matter where you draw the forces. Like any other vector, it doesn't really matter where we draw them, as long as we draw them in the right direction and roughly to the right length. So you want to draw them both on the same side? That makes you comfortable? Be my guest, okay? If that makes more sense to you. Really, it probably should be because we're pushing it, right? This would be more like pulling it with 20 newtons or 30 newtons, right? As opposed to pushing it. But it's the same thing. A push or a pull is the same thing. Is there anything else, by the way, or any other forces? Gravity is 20 times 9.81, so that's going to be, what, 196 newtons? That's a big force. Acting downwards, right? 20 times 9.81 is 196.2 newtons acting downwards. That even should be longer. I just don't have space to draw it longer. Any other forces? What's going to happen to it if this is it? Well, we know that it's going to accelerate to the right. It's also going to accelerate downward, and it's going to end up going somewhere down here, right? Well, that doesn't happen. So something else has got to be acting here. Dustin, what is it? The normal force acts with what force? What value? Well, somebody knows this. Yeah, right? 196.2 newtons. Balance is gravity, right? Because presumably this thing isn't going up or down, right? So the normal force has to balance gravity. Make sense? Yes? Perfect. Okay, you got perfect timing. It's 3:22. You got a couple minutes to just sit and rest and relax. And we have no homework tonight.